Continuing from where we left off yesterday, or not yesterday, last time, we'll say that, we talked about, or we were talking about ways to describe a function. And we had talked about two ways that day. The first way was domain and range. The second way was positive, negative, 0. So that's what we were doing last time. We're going to pick up where we left off and continue talking about the next way to describe a function. So that next way is increasing, decreasing, constant. And just like for negative, positive, 0, we're going to kind of describe these a little informally. Because mostly the skill that I want you to have is to be able to look at a graph and tell me kind of where it's increasing, decreasing, and constant. Just like I wanted you to be able to tell me where it was positive, negative, and 0. So by increasing, what we mean is that the graph is, if you're reading it from left to right, it's kind of going uphill. Decreasing, it's going downhill. And constant, it would be flat. So we'll draw ourselves a picture here in a moment, kind of talk about really what uphill, downhill, and flat looks like, but I don't think it'll be any surprise when we see the picture we draw and describe those parts. So let's say we have a graph like this. The way that I like to think about this is I imagine I have a little man that walks along my graph. He's always going to start on the left-hand side and walk to the right-hand side. I'm going to call my little man Hans, like he's a good Swiss mountain climber here. So at the start of our trip, Hans is walking uphill, right? Everybody can see that? So this section he's walking uphill. That part is increasing. Once he finishes that section, Hans is walking on a flat part. So that part is constant. And then he finishes his trip walking downhill. That part is decreasing. Everybody feel okay about what we mean by increasing, decreasing, and constant here? Juan? Always we're starting from the left going to the right. Yes, because if we went this direction, it would look like the decreasing part was uphill if we started on the right. And that's not what we mean. So always starting from the left going to the right when we're taking our little trip across our function. In general, when we're looking at graphs, looking from the left to the right is almost always going to be the preferable. Okay, so let's write down the where the graph is increasing, decreasing, and constant. When we describe where this is occurring on a graph, we're always describing the x-coordinates. And because we're describing a piece of a connected graph like this, we're describing an infinite set. So to do this, we're going to use interval notation. Everybody's okay with that idea? Okay. So if I look at this increasing interval, it begins here with the left arrow, so that's negative infinity, and it ends here at negative 2. I know that the infinity always gets a parenthesis, and for these kinds of questions, these transition points, where it changes from one type to the other, where we're changing from like increasing to decreasing or constant, we're never going to include those in any of the locations. So really, almost always, our intervals are going to be parentheses on both ends. Next, we have a constant section. That constant section begins at negative 2 and ends at positive 4. Because negative 2 and positive 4 are both transition points, they would both be included, or not included, in the constant section. And then last, we have our decreasing part. The decreasing part starts at 4, and it ends with the right arrow, so that's positive infinity. 4 is a transition point, so it's not included, and gets a parenthesis, and the infinities always get parentheses. So there's that. Everybody okay here? Sean? So this arrow is pointing to the right. The right part of the x-axis gets, the numbers get bigger and bigger and bigger. So it's positive infinity. Ignore the down part. When we're looking at describing where something's at, we're only concerning about the x part. So I just care that that arrow is pointing to the right. I don't care about it pointing down there. Does that help? I know it's often confusing. You look at the down part first because it looks like it's more down than it is to the right. But we're only caring about the left and the right part when we're doing the intervals like this. Exactly. So the left arrow was negative infinity. Yes. Good. Let's do another example of that. Sound good? Just to make sure we got it. Okay. So just like we started the previous one, I'm going to start by just identifying where on the graph we are increasing, decreasing, and constant. So how many increasing parts do we see here? 2, right? We have this first section here, and then we have this section here at the end that are both increasing. How many decreasing parts do we have? I just have one. That's this part right here. And then how many constant parts do I have? Just one. Everybody feel pretty good about that? Okay. Let's then describe where those increasing, decreasing, and constant parts are. So if I look at the increasing, I see I have two parts, so I'm going to need two intervals. So I'm going to have those connected with my union symbol. If I look at the leftmost piece, if I look at that piece begins with the negative infinity, or the left arrow, and it ends at the negative 4. The infinities always get parentheses, and the transitions between negative and positive, or increasing, decreasing, constant, always get a parenthesis. I'll then look at my other increasing part, the right one. That begins at 7 and ends with the right arrow. So that's going to be 7 to positive infinity. I know the infinities always get a parenthesis, and the transitions always get a parenthesis. Next, let's do the decreasing part. So the decreasing part begins here at negative 4 and ends here at negative 1. And I know that those endpoints are transition points, so they get parentheses. And then my constant part begins here at negative 1 and ends here at 7. And both negative 1 and 7 are transition points, so those get parentheses. Any questions here about the increasing, decreasing, and constant parts? Yes. So for these increasing, decreasing, constant parts, they're never going to have brackets. And that has to do with like the very technical definition of what we mean by increasing, decreasing, and constant that I've kind of skated over in favor of doing like something that's a little bit more practical. But increasing, decreasing, constant is technically related to slopes. So these endpoints where it changes from one to the other can't ever have a positive, negative, or zero slope because there's nothing preceding it. And that's the issue there. I know that's maybe not super clear as to why, but you're good with just never. Okay. All right. Next topic then is this idea of extrema. Extrema is a general term talking about two different things. So there's two types of extrema. There are maximums, which really that's the improper English. The plural for maximum is maxima. And there's minimums. And again, minimums is not proper English. The plural for minimum is minimums is minima. So I wouldn't ever mark you wrong for writing maximums or minimums or whatever, but I'm going to write at least the proper English. I might say it wrong, but I'm going to at least acknowledge what the correct verbiage is here and try to use that, but we all make mistakes. Everybody's okay with that. So for a maxima or minima, there's also two types of those. There are local maxima and minima, and then there's global or absolute maxima and minima. And again, I'm going to kind of skip the very technical definition of what we mean by a maximum or minimum in favor of kind of showing you pictorially, because the skill that I want you to be able to have is to pick them out from the graph and not actually do like any proof with them or whatever. Harley? Of course. So let's look at a picture here. So when we talk about a maximum, what we're really talking about is like the top of a hill. And when we talk about a minimum, we're really talking about the bottom of a valley. So if I look at the picture below, how many maxima do we see? One. Which one of them is it? Yeah, -1, 2. Everybody agree with that? That's the only top of a hill that we see. How many minima do we see? 2. They are? Yeah, -5, -3, and 4, -6. Everybody agree with that? Those are both like the bottoms of valleys. Okay? Now let's talk about what we mean by local or global. Any maximum or minimum is considered local. For a global max, it has to be the highest point on the graph. And for a global minimum, has to be the lowest point on the graph. So let's do this for our example. Let's do the minimums first. The leftmost minimum, is this local or global? It's local, right? That's not the lowest point on the graph. How about the one on the right? Local or global? Global, that is the lowest point on the graph. Everybody agree? Okay, let's do the maximum. Is that local or global? It is not global. This is local only. Why is it not local? There are points that are higher than that on the graph. Notice I did not say that it's the highest maximum. I said it was the highest point. Right? So there are, with the up arrows, there are points that are higher than that point for sure. It cannot be an absolute or global maximum. It's stuck just being a local. Everybody okay with that idea? Okay. As an aside, let's say we have a graph that looks like this. What can I say about the presence of global maximum or minimum? Can it have one? No, right? The down arrow prevents any global minimum, and the up arrow is going to prevent the presence of any global maximum. Now, it can certainly have local maxima or minima, but there cannot be a global. Everybody okay with that idea? So if you see any up arrow, that's going to prevent your global max. Any down arrow prevents your global min. Okay with that idea? Okay. That's probably all I really want to do here. that seems like a good place to stop. I want to point out to you guys